Hello, my name is Nicole Melnik, and this is my presentation for Physics 2211 Lab 2. In Lab 2, we'll be measuring an object's motion from being dropped at rest and analyze its position and tracker and in two computational models. One computational model will include only the force of gravity on the falling object, while another will include both the force of gravity as well as the drag force on the object. We'll then compare the results of the experiment as well as the predicted results of the two computational models to see how these different known forces can affect an object's position and velocity. In this lab specifically, our object in motion will be a plastic cup with a weight of 0.075 kilograms. One of the fundamental principles used in this lab is Newton's second law, stating that the net force is equal to the change in momentum over change in time. Newton's second law also states that the final velocity is equal to the initial velocity plus the net force over mass times delta t. Newton's second law also includes the position update formula stating that the final position is equal to the initial position plus the average velocity times delta t. Another key idea is the principle of gravitational force, which is proportional to the object's mass times the Earth's gravitational constant, then multiplied by the direction vector. The last key principle displayed in this lab is the drag force, which is created by the interactions of the particles in the air with the falling object. The drag force is equal to the proportionality constant multiplied by the object's speed squared. The drag force will be pushing in the direction opposite of the falling cup. With all of this, we know that net force is equal to the gravitational force plus the drag force. Here we can see the video of the experiment and tracker. The cup falling in the negative y direction is the system, while the rest of the space is the surroundings. As you can see, the object is being dropped from rest. Since the initial velocity is 0 and then speeds up, we know by the momentum principle that there is acceleration and a non-zero net force. Here's a quick scroll over the entirety of the code before we move on to what each section means. However, make note that this quick video is over the model which includes drag and gravitational force. In the following slides, we'll be comparing sections of code in both models side by side to assess their differences. The first section of the code that is important to analyze for the purposes of this lab is lines 35 through 56, which highlight the system properties and initial conditions. As you can see, the code between the two models in this section is the exact same in every line other than line 56, the proportionality constant of drag force. As stated in the lines above, a proportionality constant of 0 indicates no calculation of air resistance, so the model without drag has B set equal to 0, while the model including drag has a proportionality constant calculated to be 0.13. The next section that needs to be analyzed is the calculation loop, specifically lines 69 through 78, which are the factors behind the calculated data points. In the model without drag, we have defined our net force to be the cup's interaction with gravity. The gravitational force, or W, in line 70, is set equal to the cup's mass times the gravitational constant in the direction the cup is falling. We then apply Newton's second law, or momentum principle, as well as the position update formula, similar to what we did in Lab 1. However, in the model that accounts for drag, we define the gravitational force as well as the drag force, or FD, as seen in line 71. Drag force is set equal to the proportionality constant times the object's speed squared in the direction opposite of the velocity. We then define F net to be the sum of these two forces and insert the momentum principle and position update formula as done in the other model. Here we can see the comparison between the three modes of analysis: the tracker video's data, the model with only gravitational force accounted for, and the model with both drag and gravitational force accounted for. As you can see, the model without drag predicts the cup to fall much more quickly than the reality, whereas the model including the drag force predicts the final position much more accurately. One area of discussion related to the lab is which, if either of the models, predict terminal velocity. It is important to note that terminal velocity is defined as the constant speed that a freely falling object eventually reaches when the resistance of the medium through which it is falling prevents further acceleration. We can see that the model including drag has a flattening slope, thus implying a final velocity is reached, while the model without drag has a downward sloping velocity without any resistance to prevent further acceleration. Thus, the model including drag best predicts a terminal velocity. Another important topic of discussion is would the terminal velocity change if the cup were initially thrown downwards rather than starting from rest? The answer is no. The terminal velocity does not change. Even with a different initial velocity, the terminal velocity would still be reached just in a different amount of time. For instance, In this lab, if the cup were thrown downward as the question poses, then the terminal velocity would be reached more quickly than the cup starting from rest.